So it's a great pleasure to welcome you for today's seminar. And we have Jorge Santos as a speaker today. And he's going to tell us today about his very exciting work on this Euclidean quantum gravity path integral, understanding the canonical and microcanonical story and the new complex shadows, whether they come in or not. So we hand over now to Jorge to begin the seminar.
Well, first of all, I would like to thank Ian for inviting me to speak here today. I mean, it's really a true pleasure. Okay, so if you have any questions, please feel free to interrupt. I don't take it personally. If I don't get to the end of it, it's my problem. All right, so today I'm here to tell you about some work that I've developed in collaboration with Don Marolf, professor at UCSB. And it pertains exactly what Ian was saying. It pertains to the study of the Euclidean quantum gravity in a box, so the Euclidean path integral, okay? The talk will be mainly divided into two chunks, the canonical, talking about the canonical ensemble path integral and the microcanonical ensemble, but you'll see that, you know, many of the things that you'll see in the canonical actually will also apply to the microcanonical, okay? So more concretely, this is the menu for the talk. I'll start with the motivation. Why do we study Euclidean path integrals? It's interesting to note that our original motivations for studying Euclidean path integral are somehow outdated. They're not really valid, okay? Then I'm going to tell you about the canonical ensemble and exactly how to define the canonical ensemble. This will be probably the most intense part of the talk. And then I'm going to talk a little bit about the particular saddle that appears in the canonical ensemble, the Euclidean Schwarzschild ADS black hole, and discuss a little bit its properties, okay? We'll be mainly interested in studying the stability of the Euclidean Schwarzschild ADS black hole in the sense that I will describe as well. And I'll present the results regarding the stability of this Euclidean geometry, section 4, all right? So this is like the first half of the talk. The second half of the talk is a little bit more technical. And because of that, it will be a little bit more schematic because it's just hard to put all of the details of the microcanonical calculation. So I'll give you a little bit of the gist of what we've did, okay? But you have to look into the paper to understand all the details of what we've done. And then I'll jump immediately to the results and then to some conclusions. In the conclusions, I will also discuss some future work. Not so sure if it's future work or ambitions for a future work, but I'll let you decide. All right. So it has long been known, you know, since the work in the 70s of people here in my department, Gary and Stephen, that canonical partition functions, so let's call this Z, that are function of the temperature, are naturally described by Euclidean path integrals. Okay, so this is always gravitational partition functions, if you want. So in this approach to quantum gravity, one specifies some data at some boundaries. These boundaries could be the union of two disconnected boundaries, for instance. Let's call these boundaries just G partial dm. That's where you specify, for instance, some metric, and integrates over all fields that are compatible with the boundary data. And by here integrate, I mean literally do a functional integral to compute the partition function, okay? We're always thinking about Euclidean gravity, and that's why there's no pesky I here. There's a minus sign there. Okay, so this is just the Euclidean action. One of the earlier motivations for studying this is that perhaps this converges very fast. Okay, that was the idea because, you know, it's Euclidean, there's no I floating about there, so perhaps this converges very fast. And it should be easier to put, for instance, on a computer and perhaps study quantum gravity on a computer. Okay, that motivation is actually very bad, very, very bad. We'll soon see that even though there's a minus sign there, this object, if you insist on really working with Riemannian manifolds, is very ill-defined. Okay, we'll come to that very shortly. So let us imagine that for some theories, for instance, the Einstein-Hilbert action, you know exactly what the Euclidean action is. You take G Newton to be very, very, very small, and you can use a semi-classical approximation, and in particular, find the saddle points of this integral, which are just gravitational instantons. So these are just solutions to the equations of motion derived from this action. And in that limit, in principle, you are able to compute this partition function to some degree of approximation, okay? And that's what we do for a living. In many cases, we solve the Einstein equation with some nice boundary conditions, some Euclidean problem that can be complicated, we put on a computer, and we go on with our lives. Now, this school of thought predates ADS-CFT. You know, it's kind of crazy if you think a little bit about it, because there's a certain sense where ADS-CFT gives some backbone to this story. Because in ADS-CFT, we have concrete realizations, if you want, of Euclidean quantum gravity, because you can do a bulk calculation, compute several saddle points, see the dominance of these saddle points changing, and it brings some beef to this story. A crucial example that was understood by Edward in the early days of ADS-CFT is the Hawking-Page phase transition in the 1998 paper of Edward Witten. But you know, if the whole story was just saddles, this would not be a very interesting talk. Well, it might still not be a very interesting talk, but I'll let you decide that. But if it was just the saddles, we would be missing quite a bit. Because, you know, not only you want to have a saddle, we want that saddle to dominate, and you want it to be stable in some sense. So you want to see how that saddle reacts to small perturbations. We want to see if it's really a minimum of the action, or if there's a direction over which this path integral actually diverges. So it's a statement we would like to understand the one loop determinant around the saddles. Because if the one loop determinant is sick, for instance, it's not convergent, we should not be studying that particular saddle point. All right, so we're interested in the notions of stability of these saddle points. Now, for those of you that have followed a little bit the literature, you should be shouting all over the screens, saying this guy is completely crazy, because we know that this Euclidean path integral here is completely unbounded from below. Okay, we know that this is not going to converge. Okay, and let me show you rather explicitly that that path integral is not going to converge. Let us imagine that you start with the Einstein-Hilbert action. Okay, here it is. There's this boundary term to make sure that the variational principle is well defined. This K tilde is just extrinsic, the trace of the extrinsic curvature. This H tilde is the induced metric on the boundary of my manifold. This R tilde is just the Ricci scalar, and this G is just a determinant of the metric. Okay. Now let us perform some conformal rescaling. And so let us demand that G tilde is equal to some factor of omega times G. And it is our job, and it is your job to go home and see how this action behaves under this scaling. All right. What I want to show is that this omega that appears here will appear as a scalar from the perspective of this action. And that scalar will have a kinetic term with a wrong sign. All right. That's what I want to show. The wrong sign. So it will not have a minus sign, it will have a plus. And that's exactly what you find. You find that if you do this conformal rescaling of the metric, now omega appears as a scalar field, but unfortunately, this is a plus sign. And that means that this action is completely unbounded from below. Okay, so we know that we cannot just, Euclidenize our metric and search for Riemannian manifolds. That is not going to do the trick, because this action is completely unbounded from below. So our original motivation of having a path integral that might converge is just not true. Is this message clear? I see I am nodding, so I'm going to assume that this is true. So this prevents one from taking the integral over all Euclidean metrics as defining the problem that we want to study, computing the partition function because of this problem. So we know that the metric, there will be bits that will have to be somehow weak rotated, complexified in order to make that metric, that path integral convergent. Okay. Of course, you can just say, actually, we want to do something completely the opposite of this. What you should really be doing is starting with the Lorentzian signature path integral, okay? Because there, everything converges. It doesn't converge if you put it on a computer, but it always converges in the distributional sense, right? If you look at this integral, e to the ix, dx to the k here, right? This integral as a distributional representation is delta k. So if you have an I there, this integral will always converge in a distributional sense, okay? So let us imagine you do that. And let us imagine that somebody, yes?
Jorge, can I ask something already? Suppose if I make the same discussion in the context of, say, the no boundary proposal, where I'm preparing some wave function using Euclidean path integral. So there also you would say, even if I have some real thing, you will also like to say that you have to consider the complex saddles necessarily, or you have the same issue that you have to look for.
Yeah, you have to look. You always have to look for complex saddles, and then even in this approach, you might have to look for complex saddles. Okay, and then what you have to do is to try to understand. You have to try to understand. You have to then try. You then have to try to understand the analytic structure of your integrand. And once you understand the analytic structure of the integrand, then you ask, okay, I have the saddles. Are these saddles relevant for computing my integral or not? So can I find a curve of steepest descent that passes through those saddles and is homotopic to the contour that I started with? But the first question is you find the saddles, right? Even in Lorentzian signature, you find all the saddles. You start with some defining contour, which is something that say string theory gives. And now the question is, can I deform this contour to go through my saddles or not? And once they deform to go through my saddles, can I actually find a sensible result?
Yeah, but my ninth question was actually, how do you define things like no boundary proposal with complex saddles?
I think you define it in the same way. There's a contour. There's a contour, and once there's a contour, you search for saddles. It's defined in the same way. What I'm not telling you is what is the contour that you should choose, and nobody knows, because that's essentially a UV question.
So essentially, you would look for any kind of metric which is regular, which fits this boundary condition.
Exactly. And then once you have those metrics, there's a really hard job that you don't know how to do, okay? Which is, which of these metrics that you found is actually relevant for computing the integral that you started with. You see, you start with a contour, then you use Cauchy's theorem to deform this contour to be such that it goes through a path of steepest descent, if it's possible. Once it's on that path of steepest descent, then you perform the saddle point approximation and you capture the saddle that you want. The question, the problem that you might arise is that you might hit singularities before you get there. There might be branch cuts that have physical meaning, but we don't understand the analytic structure of the Lorentz signature path integral to be able to tell you, yes, you can do this, or no, you cannot do that. You see, we just don't understand it. But that's, it's a bit like studying a integral in complex analysis and on steroids. Instead of being a finite dimensional integral, is now a more complicated thing. That was an excellent question, thanks. Now, in this latter approach, where you actually start with the Lorentzian path integral with a particular contour, the implications for the Euclidean path integral are discussed and investigated a posteriori. It's like, we start with something that is always convergent. We find the path that makes this as Euclidean as it gets, and that will give you the information about the Euclidean path integral. So what I'm trying to say is that, it would be amazing, nobody knows how to do this, but it would be amazing if you could deduce the Euclidean path integral in gravity from the Lorentzian path integral. This is possible to do, for instance, for Young-Mills. Everybody knows how to do this in Young-Mills, but in gravity, we just don't understand enough about the analytic structure of the path integral. Perhaps, we could do something crazy and go to in the case that there's an ADS asymptotics, go to the CFT, understand the path integral there, the analytic structure of the path integral, and then come back to gravity and deduce something about the Euclidean path integral. But, this is all just words. Nobody knows how to do this, okay? So while I'm deeply sympathetic to this perspective that we should always start Lorentzian, it does really not give us any useful recipe to determine the stability of the Euclidean saddles, because nobody actually knows how to do this. What is the contour that you should pick? So instead, we're going to do something a little bit different. We're going to look instead at local statements. We're going to take a saddle and ask, how can you make sense of the path of steepest descent locally? Okay, we're not going to show that it can be connected to some grand contours postulated safe by string theory. We're going to just do a local analysis to study stability. And even that is going to be complicated, I will argue. Okay. Now, you might ask, so what have people done in the past? Because, we've been talking about Euclidean path integral since the 70s. This didn't stop there. So what have people done in the past? Well, in the past, for certain particular contexts, what these gentlemen have done in 76 is to say, let us just weak rotate the conformal factor. That guy is giving us trouble, okay? So instead of having omega, let us imagine that there is a path for omega in the complex space of solutions that runs parallel to the imaginary axis. If you do that, then that plus becomes a minus, right? And now everything is convergent and you should go on to your merry life, okay? And in fact, this is exactly what we do in ADS-CFT. In ADS-CFT, or when we're computing these Euclidean path intervals in asymptotically flat, you make the conformal factor to run, or you integrate the conformal factor along a contour parallel to the imaginary axis, so that that plus sign becomes a minus, and you demand that the conformal metric, the rest, should be real. Okay, so you divide your path integral in these two directions. And that's what we usually do. Now, this recipe for some is mathematically elegant, okay? And it reproduces physical expectations. So let me give you a physical expectation. We expect the Euclidean saddle of the Schwarzschild black hole, for instance, corresponding to a Schwarzschild black hole, with asymptotic flat boundary conditions to be unstable, okay? Why do we expect it to be unstable in the canonical ensemble? That's because the specific heat of the Schwarzschild black hole is negative. And because it's negative, we don't expect the Schwarzschild black hole to be a stable saddle in the canonical ensemble. And in fact, this is exactly what happens in this context following this prescription. If you follow this prescription, you will find that the Schwarzschild ADS black hole, sorry, the Schwarzschild black hole, not ADS black hole, is unstable as a negative mode interpretation function. So the conformal factor is okay. That guy never diverges, but then this conformal metric, what remains there still as a negative mode. What's even better is that you expect that negative mode to go away when you go to ADS. If your black hole is sufficiently large, then everything should be stable. And if you follow exactly this recipe, that's what you find. You find that the negative mode disappears when the specific heat becomes positive, exactly at the value where the specific heat becomes positive. So this recipe, though it's very ad hoc, seems to make sense. Okay. Why does it work? Okay, or when can it work? It can work when somehow the fluctuations that are causing you trouble decouple from the ones that do not cause you trouble. Okay, so if you can weak rotate the conformal factor without having to worry at all about the conformal metric, you can do this prescription and hopefully everything will work. Okay, but when you cannot do this, when somehow they couple, it does not make sense to weak rotate one and not weak rotate the other if they're coupled. Okay, so when can they couple? Well, they couple generically as soon as you include matter.
Morning we can read.
Is there a question? No. They couple together. They couple together whenever you include any form of matter. Okay, any form of matter will spoil this recipe. We will not know how to deal with this recipe in the general sense. Any form of matter will spoil this. But even with pure gravity, there are ways of spoiling this recipe. Okay, so one of the central questions for the first half of this talk is the following: what should we do when the pure trace and traceless fluctuations do not decouple? If you cannot decouple the behavior of the conformal factor from the conformal metric, what should we do? We know that we can no longer weak rotate them separately. So what should we do in that case? Okay. What is the simplest example that I can provide where there's no decoupling? The simplest example I can provide where there's no decoupling is when you consider gravity, pure gravity, inside the box. So instead of going all the way to asymptotic flat or all the way to the conformal boundary of ADS, I will stop at some radius, okay? And ask questions about stability for the metric inside that cavity, all right? Now, I'm in the mathematics department with a lot of mathematicians whose only job is to study the Einstein equation at the very formal level. And if you tell them that you're going to solve the Einstein equation inside a cavity, they get mad at you. They get seriously mad at you, okay? There are very, very active discussions, I cannot tell you how active they are, as to what choice of boundary conditions you should have on the cavity wall that leads to a well-defined mathematical problem, okay? There's extremely, let's say, active discussions about this. This applies in the Euclidean setting, but also applies in the Lorentzian setting. For instance, we do not know what are the boundary conditions that I should impose on our cavity to have a well-defined initial value problem in the Lorentzian sector. We don't know. We know that some work, but we know that some others are very unlikely to work. In the Euclidean setting, this is also true. There's early work by Anderson, and there's much more recent work by Edward Witten. And it's not trivial what boundary conditions you should impose in order to have a well-defined elliptic problem on the cavity walls. Now, for simplicity, we're going to take the simplest possible type of boundary conditions, which, funny enough, is very unlikely to work at an unlinear level. Okay, we're going to demand that the induced metric on the cavity wall does not change. For all sorts of reasons, there's strong belief that this does not lead to a well-defined initial value problem. Okay, just doesn't. And this is explained here in this paper. There are changes to those boundary conditions which seem that they have a chance to work, but you don't fix the whole metric on the cavity, you just fix the conformal class. And then you fix the traces of the extrinsic curvature. Okay, and those have a chance of working. Fortunately, for the purposes of this talk, we tried those boundary conditions and those boundary conditions. The numbers change, but the overall picture doesn't. Okay, it's still true. Whatever weirdness I'm going to find, you find with both of types of boundary conditions. Okay, good. All right, so let us now move on to the canonical ensemble. So in the canonical ensemble, we work at finite temperature. Okay, finite temperature in the Euclidean setting means that we want to consider spacetimes that are of the form, say, S1 cross some other sphere with the higher dimensions. And we want the boundary conditions to be such that this S1 does not change radius. That's what controls the temperature of my system. Okay. And in particular, we are interested in addressing the stability properties of the gravitational instantons in this setting. But you should be very worried, because I keep telling you about stability, but we're in the Euclidean setting. There's no Cauchy problem. It's an elliptic problem. So what the hell do I mean by stability? Okay, and I want to make this very precise. Consider an Euclidean path integral, for instance, this one. Okay, it has some metric, but let's imagine there's also some field, some scalar field running on it. Okay, let us imagine that you have a number which is very large, for instance, 1 over G Newton, and let's call that number n squared. Okay, so we want to take n to be large. There's no AVSFT here. I just want this n to be large. Okay, and let's imagine that this n squared is 1 over G Newton. All right. So if that is very, very large, I can use the saddle point approximation. There's a very large fluctuating phase here. And what does this saddle point approximation give me? Okay, well, it gives me a piece which is just ion shell action evaluated on the classical solutions to the equations of motion derived from this action. And then there's a quadratic piece here. Okay, there's no first order piece appearing because these are truly honest to God gravitational instantons. That means that they're actually solutions of the classical equations of motion, and that's why there's no linear piece. So this is a quadratic thing on this delta G and delta phi, which are fluctuations. So this beast here is the one loop determinant, which has to converge. Okay, good. And I stress that there's no first order piece because we're looking literally at classical equations of motion. So to put it very clearly, stability means that we want this object here, this second order action, to be positive definite. Okay, so such that this integral here converges. All right, so that's what we mean by stability in the Euclidean sense. Is everybody happy with this? All right. But again, for the usual just Einstein-Hilbert action, this does not work. Okay, you study that second order piece, and you find that the trace modes, which are the modes that are associated with conformal transformations, just diverge. And what this gentleman said we should do is to just weak rotate. Send H to IH, then everything will converge. Now, the reason why I'm actually showing this up here is that, for many years, this was a complete conjecture, right? People just thought, this works, but there's no reason to believe that this works. But because of ADS-CFT, we can compute the partition function in gravity, and we can compute the partition function on the CFT, okay? And ask, will they agree or not if we follow this prescription, okay? And the answer is they do agree if you follow this prescription. For instance, there's papers by Diosaninos and collaborators and Kotler more recently, which show that you can do a field theory calculation, compute the partition function in the field theory calculation either using something like localization or something like that, and it will only agree with the path integral on the gravity side if you actually do this weak rotation. So there's evidence that this is the right thing to do. But in these cases,
sorry, I
no
didn't get this
gravity.
statement. So what do you mean by the field theory computations in this context?
Yeah, there are cases where you can actually perform compute the partition function on the field theory side, okay, using some clever technique.
Dual field theory side?
On the dual field theory side.
I see.
And then they will only match the gravitational thing if you do this this business. Okay, so this gives you evidence that something is correct. But in all of these examples, all this falls in this class where the conformal transformations decouple from the rest of the metric. So cavities are not included in these examples at all. Okay. Now, this slide is a little bit technical, okay? But we are going to take a different approach. And because we are going to take a different approach, I necessarily have to show you what we're going to do. And that's why it's a tiny bit technical, okay? So let us imagine that we go to second order in the perturbations. And for simplicity, let's look at the Einstein-Hilbert action, okay? So no scalars whatsoever. Then I'm trying to show you what the action looks like at quadratic order, okay? Remember, there's no first order piece because we're assuming that the background equations are satisfied. At quadratic order, it turns out that you can write the second order piece as an expectation value. This is not obvious that you can do, but it turns out that you can do, okay? It's an expectation value. There's an inner product here defined. That's what defines your expectation value between two objects, H and LH. I'm not telling you yet what L is, but I'm telling you what the inner product is. This inner product takes this form, okay? There's a natural metric that appears there, a metric on the space of configurations. It's a particular member of the DeWitt metric. So DeWitt metrics are metrics that appears on the space of configurations, on the space of metrics that are ultra-local. They do not depend on derivatives, okay? In the literature, if you dig up what the second order action looks like, almost everybody writes it in this form, okay? Now, this is a particular DeWitt metric. The most general DeWitt metric that you can write down is this one, where there's a free parameter here, okay? This falls on a particular DeWitt metric, where this lambda DeWitt is -1. There's a reason why it's -1, and why everybody has worked so far with -1, because this makes the orthogonality between physical modes and gauge modes apparent. But there's a priori no reason why you should choose lambda DeWitt to be -1. Okay, but that's what people write in the literature, and that's what we're going to run with it. If you indeed have this being lambda DeWitt -1, okay, and this L, this operator that acts on metric perturbations, turns out to be very familiar. It's just the Lichner-Ovix operator, okay, shifted by some bit. That's it. And now you can see why people tend to choose this metric on the space of configurations, is because this, if you choose the Donder gauge, this will be 0. And the operator that you're left with is exactly the Lichner-Ovix operator. Is this clear? All right, good. So in this language, where is the conformal factor problem? In this language, okay? The problem is that this inner product defined by this metric here, okay? This inner product here between two metric perturbations is not positive definite. It is in fact negative if you look at trace dominated perturbations. So there's a natural expectation value that you can write down, but the expectation value uses a certain inner product, which is not positive definite. There's an indefinite signature. Without a finite cavity, somewhere in the middle, the trace and the traceless modes decouple, okay? So we can weak rotate the trace modes only. And if you weak rotate just the trace modes, this metric actually becomes positive definite and leaves this operator here, L, self-adjoint. So if you want to understand whether there's a instability or not, all you have to do is to study the spectrum of this operator, L, and you're done. Okay? Is this clear? So in general, the metric does not have a definite signature. After weak rotation, it has a definite signature. This operator remains self-adjoint. So I just study the spectrum of the operator, and I'm completely done, because that's what tells me if this is positive or negative. All right, and you can do that so long as the trace perturbations decouple from the conformal metric. But this is not the case if you have a cavity. Yeah.
One question about this. So this self-adjointness is also critical for the bound. I mean, only if you choose the Dirichlet boundary conditions where you're fixing the conformal class in the boundary.
No. You'll see that it's delicate, and it's funny that you're asking this because it's going to be the next slide. It's delicate. It's very delicate. The first time I saw this problem, I thought exactly what you're thinking. It turns out to be delicate. Wait 1 minute. So let us now introduce a cavity. The cavity will couple the boundary, the induced metric on the boundary with the trace modes and the traceless modes. Okay, so they will have to couple the trace and the traceless modes now. Okay, how do you see that they have to couple? It's very simple. If you just try trace modes, okay, or if you just try the traceless modes, it would seem that they would want to move the cavity. You need to add a trace mode to make sure that they don't. Okay, there's a linear combination of the two that you necessarily has to be non-zero, okay, such that the induced metric, does not move on that cavity. But this is a problem, because if you weak rotate one, you should also be weak rotating the other, or else 1 plus I doesn't cancel. It's only 1 minus 1 that cancels, not 1 minus I. So you cannot weak rotate one without weak rotating the other. But this scares you, because all of the procedure that we've seen before was based on this weak rotation, which we can no longer perform. Okay, so you cannot. It's nonsensical to weak rotate one without weak rotating the other in this context. Okay. What is the key observation which will allow us to make progress? The key observation, again, is that we can write these second order perturbations as an expectation value of something, okay? And that's what we have to use to make progress. In particular, if you give me the width metric, and I'm going to use the one that everybody uses, okay, and then comment on this in the end. If you give me the width metric, then I can read off what this L is in general, okay? And for some reason, okay, what this L is in general. So you first choose the width metric, that chooses the inner product, and then you read off what L is, okay? So let us imagine you do this. Does this L satisfy nice properties? Okay, I'm not weak rotating whatsoever at this moment, okay? And it does. One is that L is diagonalizable. This is a little bit non-trivial, but not too non-trivial, okay? It's diagonalizable, that's good, okay? But in general, it turns out that L has complex eigenvalues. And as Ein was saying, this might suggest that you have a problem with your boundary conditions, that the problem somehow is not self-adjoint, and that's why you're going to get complex eigenvalues, okay? But that's not the reason why you're going to get complex eigenvalues. It's because of something else, okay? And I'm going to try to convince you of that now. But I hope you understood the spirit. So you have a quadratic operator, okay? You first define the inner product. Once you define the inner product, then you can read off uniquely what is the operator that controls the stability properties of this quadratic form. But first you need to tell me what is the inner product that you're going to use, okay? Good. Our prescription is completely general, and as far as I understand, completely new, okay? So I'm going to take a little bit of time to explain what is a generic prescription that we're going to use. The action that we're going to use is quadratic, right? It's by definition is a quadratic action, okay? Now let us imagine that you want to write down a nice discrete approximation to this action, okay? You use whatever approximation you want to use, you discretize it in whatever way you want to use. You can use spectral operations, you can use finite differences. Let us just imagine that you discretize that action. The claim is, after you discretize that action, it can always be written in this form. It's a number, which is literally just a sum over a quadratic form, where this represents the second derivative of the object. So whatever you do, whatever discretization you use, okay? You can always write the action that I've shown you before as a sum like this. If you're a little bit confused about this, just remember that these sums in the right limit will give you integrals. Now, all I'm saying is that you can always discretize those integrals, okay? So this is a discretized form of the action that we've seen before, okay? Good. Let us imagine that qi equals to 0 is a stationary point, and that you want to understand whether this guy is positive definite or not. That's your job. Do you understand why this still represents a quadratic action? I'm just assuming that my integrals can be discretized in some manner, okay? Good. For pure gravity, we know guaranteed because of the conformal factor problem that this S here is not going to be positive. Is not going to be positive if you take the QIs to be real. Just not going to happen. Forget about it. Okay. And that's why we weak rotate. So in this language, what is a weak rotation? That's what I'm going to try to understand. What is a weak rotation in this language? A weak rotation is just a map. So you take your QIs, okay, you dress them with a matrix, and you introduce some new variables, R, okay? And it is your job to choose these WIs. For instance, I'm going to give you an example. The case where everything decouples, you can choose this W to be I only for the trace modes and to be 1 for the non-trace modes, okay? And this will do the job. This is one form of the weak rotation. But in general, we don't know what it is. If you have a generic perturbation. The only thing we know is that there's a matrix, which is complex, and I want to keep these guys real. And it's this matrix that tells me how I'm going to perform the weak rotation. I haven't specified it yet, okay? So all you have to do is to take this form for the Qs, introduce there. And I haven't told you yet how you're going to write the W's that you should choose. That's part of the problem, okay? Once you do that substitution, now you have to study the positivity of this object for R real. These W's can be complex, but these R's are real, okay? If they are complex, all of this has to be in such a way that this S check will still have to be real. All right, how do you choose these W's, these matrices? Well, we want to choose them in such a way that the weak rotated metric, the weak metric is positive. That's what we would like, right? Because then everything is positive and then I'm done, okay? So we want to choose these guys such that the weak rotated metric is positive, okay? In the spirit of weak rotations, we want to be able to do a weak rotation and undo the weak rotation. So we want to choose these guys to be invertible. And it might look that we're done. But it turns out that these properties alone...
Is W a constant matrix or it's a field dependent?
Good. It will turn out to be constant. It will turn out to be, well, you'll see. We'll write it in an invariant form, but you can choose them to be constant. Yeah, it could be, for instance, I for some component. Yeah, remember they're only after the sign. Yeah, but that's a very good question. Very good question. So how do we proceed? How are we going to choose these W's? Okay. Well, this is the bit where you need a little bit knowledge of linear algebra, but you don't need much. Okay, it's not very profound. First, we need to define an inverse metric. Okay, so you need to take a metric which is the inverse of the DeWitt metric. Once you have that inverse, you can construct an operator. Okay, so you act on this second derivative kj with this inverse metric. This defines an operator. What is the beauty about this operator? This operator is always self-adjoint with respect to this G. Why is it always self-adjoint? And go home and check. It's always self-adjoint with respect to this G because this is a second derivative here. Because there's a second derivative here, these second derivatives will commute, and this guy will always be self-adjoint. So you can always construct a self-adjoint operator if you're reading off a quadratic form. Did this sink in? So I'll give you a quadratic form, you will give me a metric, and out of this, I can always, irrespectively of this quadratic form, construct to you a self-adjoint operator, okay? And it's now the eigenvalues of this self-adjoint operator which will control everything for us. All right. What are the assumptions to proceed? We're going to assume that this self-adjoint operator is diagonalizable. Okay. In particular, that it spans the same eigenspace as the cubes. You might be looking at me and thinking, this guy does not understand a thing about linear algebra, because if an operator is self-adjoint, well, it's always diagonalizable, right? That's what you learn in kindergarten. But that's not true, because the metric that we chose is not positive definite. Because the metric that we chose is not positive definite, it's not true that self-adjointness is enough to show that this L is diagonalizable. It's just not enough, okay? Except that the metrics that we tend to choose are positive definite, but this one is just isn't. This is something that has to be checked. You construct this guy for a particular G, for a particular action, say the Einstein-Hilbert action, and check, is this diagonalizable or not? It turns out it is. Okay. Now, remember that G is not positive definite. The metric that we chose is not positive definite. And that's why the eigenvalues of L can in general be complex. This might look strange, right? This might look strange because usually we think if we have an L that is self-adjoint, an operator that is self-adjoint, then it will have real eigenvalues. But careful with that statement. It has to be self-adjoint with respect to a positive definite metric. With respect to a positive definite metric. If it's not positive definite, it's not true at all that the eigenvalues have to be real. And this is something that for some reason we don't learn very well, at least here in England, in linear algebra. You always have to choose a positive definite metric before you can make this statement that if L is self-adjoint, then the eigenvalues are necessarily real. Okay. And let's just give you a brutal example so that you see that I'm not lying to you. All right, start with this one, lambda 1 star V1, V2. Okay, that's the same as L acting on V1. Now it's self-adjoint, so I can exchange the V1 in the V2. Now L acts on V2, and so I get L lambda 2, right? This bit we all do in linear algebra, right? Good. Now take V1 is equal to V2. Look at the first and look at the last. Well, there are two options. Either V1 is different from 0, and then it's true that lambda 1 must be equal, lambda 1 star, sorry, must be equal to lambda 2, which must be real, and we're good, right? Because there's an equality of this with that. But because the inner product is not positive definite, it could well be that V1, V1 is 0. And then look, if V1, V1 is 0, this guy is 0, and this guy is 0, and you do not reach any contradiction whatsoever. Okay, so that's the second option. If V1, V1 is 0, which can happen because our metric is not positive definite, then lambda can be complex.
So does it follow that if you have complex eigenvalues, their eigenvectors have 0 norm?
Yes.
Okay.
It does follow. Absolutely. Absolutely. Fantastic. Yeah, that's spot on. And you can check. All right. So what is the rule of thumb? Okay. So V, V can be 0, but you can prove, because the metric is non-degenerate, that V, V star is never 0. Okay. So V, V is, but V, V star is never 0. Okay. That's easy to prove. So let us choose. That means that, there's a normalization factor that we have to fix somehow. We have to normalize your eigenvectors somehow. And I'm going to normalize them such that V, V star is equal to 1. That's a very convenient choice. Assuming this choice, it's a choice. Okay. Assuming this choice, what is the rule of thumb? Well, we're going to require that our weak rotation is such that if lambda is real, and if the norm of the eigenvector is positive, then W should do nothing to the eigenvector. Okay, that's the,
sorry.
that's the
when you say that you're choosing V, V star is equal to 1, that means you're choosing your David metric in this way.
You're not choosing a metric. You're choosing a normalization for your eigenvectors.
Oh, sorry. Okay, you're just choosing a normalization for the eigenvector. Sorry.
Yeah, it's like there's the freedom to multiply by a complex number, and you're multiplying such that this is 1. If you do this, there's some nice properties about the real part and the imaginary part. You see, otherwise it's not well defined to talk about the imaginary part and the real part of an eigenvector, because if you multiply the eigenvector by a complex number, it will still be an eigenvector. So you need to fix a normalization somehow. So if the norm is positive, okay, and if the eigenvalue is real, the weak rotation should do nothing to your mode. Okay, good. If the eigenvalue is real, but if the norm is negative, then the weak rotation should give you a minus sign. How do you do that? Well, it's an eigenvector, should be an eigenvector, this guy with an eigenvalue of I. So in some sense, what Suresh was arguing that it's a constant matrix. Yes, you can make it constant. It's such that you multiply by I in this case. What about the case that is more interesting? What about the complex case? What the hell do you do? Well, as I just said, you gave like a meaning to the real part of V and the imaginary part of V by demanding this normalization. With that normalization, okay, you will choose things such that the real part should be left invariant and the imaginary part is multiplied by I. That's what you should do. With this rule of thumb, which we cooked up, that's why we call this rule of thumb, we cooked this up, what can you prove? Well, if all the real part of the lambdas are positive, then we can prove that this quadratic form is positive. It's stable. If at least one is negative, we can prove that the saddle is unstable. There's the case of marginally stable. And what's most beautiful about this, if you follow a little bit of the literature, is that this rule of thumb is completely consistent with stability under Ricci flow. If you don't know what this is not gonna help you, but it is consistent with stability of Ricci flow. Okay. It would be amazing if we could deduce these rules from a grand scheme, from the Lorentzian path integral. We can't yet. We would love, but we can't.
So, I mean, will the functionals of Perelman play any role in doing this?
Sorry?
You know, Perelman used, in proving the Poincare conjecture, right? He had constructed this functionals, I think entropy is what he called it, but can it come from that kind of approach?
It can be used in that kind of approach, and indeed it has been used in the past in that kind of approach. But I don't think it can be deduced.
Okay.
Which is what we love. To deduce this, you need to start with something convergent, like the Lorentzian path integral, and then see that this is indeed the path of steepest descent. But we don't understand the path integral enough to be able to deform this into a complex plane, or at least I don't.
And just one more question. So, but this is the Wij is specific for the saddle point that you're studying.
Good. The Wij in this prescription is attached to the norm of V, and the V depends on the saddle points. But I'm not attaching this to the saddle point. It's like to the V's, to the eigenvector. The eigenvectors decide. If they have negative norm, you do something. If they are complex, you do something else. And if they're positive norm, you do something else.
So then I have a question. If there are multiple saddles, how do you check that your choice of Wij works?
Amazing. The choice of Wij will always work because it's only associated with the eigenvectors of the saddle. But what you're asking is, I think, a much more interesting question, which is, how do you know which saddle is relevant?
Yeah, okay, maybe.
But that's a much more difficult question, because that I would have to start with the definite contour and check which one is the path of steepest descent. And sometimes you can deform on some saddles, sometimes you find obstructions. Okay, if there's more than one that do the job, then by Cauchy's theorem, they have to give the same result. Because Cauchy's theorem tells you that if it's analytic, you're going to get the same result. Good.
But I mean, one thing is, so Wij is actually dependent on the particular choice of the saddle. Right? Which saddle, Wij will not be the same for all saddles. No?
No, it will depend. It will not be the same, but it's dependent on the norm of the eigenvector. And of course, the norm depends on G, and the G depends on the saddle. I agree with all of that. But you can check that this recipe that we gave here works for a very large number of saddles. It does what you expect the thermodynamics to do in a large number of saddles. Okay, inclusive. Well, I should not talk about the unpublished work. It worked for a bunch of them. Now, there's one thing that I've not discussed whatsoever, and it's the bulk of the paper. Check it. I've not told you anything about gauge invariance, and I'm not going to tell you. It can be dealt with. Okay, good. So what do we do? Well, let's test if our proposal is correct. Okay, So this is Euclidean Schwarzschild ADS. Everybody knows the metric for this. We require that there's no conical singularity. There's a bolt located at R equals R plus. And there's a conical singularity there, unless I identify the temperature, this beta star, which is the periodicity of tau, to be exactly given by this. Okay, everybody knows this. Note that this beta star is not the physical or the inverse physical temperature as measured at a cavity wall, because cavities have not been introduced. Okay. Now let us introduce a cavity just now. Okay. Well, if you introduce a cavity, then you don't consider all of that line element. You just consider that line element restricted to R smaller than R naught. And now the temperature is redshifted. There's this factor here, this pesky factor there of R naught, because the temperature is redshifted. Can go home. This is a standard calculation that we give our undergraduate students to do. For every fixed value of beta star, there are two black holes, a large and a small one. The large black hole has a positive specific heat, the small black hole has a negative specific heat. Okay, we can determine the separatrix between these two things as a function of all black holes and as a function of the cosmological constant. And we expect the negative modes to stop existing, or stability regions to be such that if the negative specific heat is the specific heat is negative, it should be unstable. If the specific heat is positive, it should be stable, right? Well, let us see what we got. We'll only discuss here the spherically symmetric modes. We can generalize this, okay? And we find, first thing, that the lowest lying mode, okay, has positive norm. So the weak rotation should do nothing, okay? And is real. Rule of thumb tells us that it should not be weak rotated. All right, and here it is. It's not weak rotated. It becomes negative in a certain region. This separatrix here, which tells you when it goes from negative to positive, is exactly when the specific heat changes sign. So our rule of thumb is doing exactly what it should. Okay, this matches exactly expectation. These plots could have been produced many years ago. The only thing that people have not done before is to check that all of these modes have a positive norm on the G hat. But this would not be exciting. What about the excited modes? This is just the lowest lying mode. What about the excited modes? Things are way more interesting here. In this case, we find real and complex modes, and they merge and split as a function of the parameters. It gets complicated. Look, here I have, for simplicity, I have zero cosmological constant in this case. I have the radius of the cavity here. Why not? This is the real part, and there's a bunch of color coding here, okay? The greens just means that the modes are complex, okay? The blue means that the modes have negative norm, and the red means that the modes have positive norm. And what we find is that the modes with negative and positive norm merge, for instance here, give rise to a complex mode, okay? And here is the complex mode, and here they become, again, different from each other. And there's this nice interchange between being complex and real as a function of the parameters. If you turn on the cosmological constant, there's one more dimension in which all of this get messed up, okay? There's also some black lines here that has to do with gauge invariance. Check the paper, okay? It's complicated. And these modes have never been uncovered in the literature whatsoever. We were the first ones to find out. Fortunately, they all have a real part bigger than zero. So they don't tell us anything. They just tell us that everything is stable. The last few minutes, very few minutes, I'm going to tell you what happens in the microcanonical ensemble. In the microcanonical ensemble, things are a bit more complicated because we first have to understand what the hell do we have to keep fixed. For the canonical ensemble, it was the temperature that we had to keep fixed. And that's the Euclidean circle that you have to keep fixed. So that's a boundary piece that you have to keep fixed. What about the microcanonical ensemble? What do you keep fixed? Okay. We would like to import as much as we know from the canonical ensemble to study this problem, because there's, loads of work on this problem. And in fact, there's a lot of work on the canonical ensemble, and there's absolutely no work on the microcanonical ensemble. I'll challenge you, okay, to find any work for studying Euclidean Schwarzschild black holes in the microcanonical ensemble. Eventually, you'll find one. After a long work, you'll find one, okay? But that one, the result makes no sense. It tells you that it's unstable in the microcanonical ensemble. But if this goes completely against the results that we have for dynamical stability, I can show that dynamical stability will make you believe very strongly that the Schwarzschild black hole has to be stable in the microcanonical ensemble. But it really seems that you won't have this opportunity because all of the modes that we've discussed before decay so rapidly at infinity, okay, that it would seem, in fact, decay exponentially rapidly. It would seem that if they're there in the canonical, they have to be there in the microcanonical. And it can't be. They cannot be there in the microcanonical ensemble, or else our expectations, for instance, for identifying the entropy would just be wrong. Okay, so what the hell do we do? This is a long story. Okay, it's a long story and I don't have time to cover it whatsoever. But the idea is that there is a way of reading off the microcanonical partition function from the canonical partition function via an inverse Laplace transform. Okay, now not everybody knows about this. Stephen actually knew about this. Read his early papers. This is all written there. Okay, so let me tell you a little bit how this arises. A canonical ensemble partition function is supposed to compute this sum. Okay, now let us think about another sum. Okay, let us imagine that we analytically continue beta in this manner. Okay, introduce some weighting function, and this is a parameter. And now let us think about this integral. I just told you, think about this integral. Okay, well, you know what z is, you substitute it there, and you perform the integral. What you get? You get this sum. You can do the integral, and instead of starting with this weighting function, you just get its Fourier transform. Now you imagine that this weighting function is very, very, very localized, okay, such that you only pick states with e equals e naught, and you get the microcanonical partition function. And the integral that I wrote is essentially in the limit where the weighting function gets very, very, very thin. It's essentially the Laplace transform of the inverse Laplace transform of the canonical ensemble. So the procedure
how is this different from how we usually prove the equivalence of ensembles? And the Legendre transform? It's not that?
It's not. You were good. You know, you're working with systems where the canonical, where the ensembles are just not equivalent, because the specific hits can be negative. So you cannot. It's not as easy as a Legendre transform in this case. That's partially the problem.
Yeah, but I usually thought that when this fails, it's like one description is not good.
It's not known. It's just dealing with different physics, as I will show. It's not necessarily that. It just means that you have to be careful. They just correspond to different situations, different physical situations. So we do this exact same integral, exactly the same integral that we've done just a minute ago for a standard statistical system we do now. Okay, it's exactly the same thing. Look, the contour is the same, but here comes the rub. If you really want to identify the microcanonical partition function and the microcanonical action, what we should really be doing is exchanging these two integrals. Perform first the t integral, and then with that read off everything from the microcanonical perspective. It's hard to do this t integral. It's very formal, and it's the first 5 pages of our paper. It's how to do this integral in t first. And you have to move to conical singularity. It's not trivial how to do that integral, but I'm not going to tell you how you do it. I'm going to tell you what the result is. The result after doing this integral in t is that you have to consider configurations with a certain, where a certain definition of off-shell energy is conserved. So you do this integral and you find that you should only sum over configurations for which an off-shell energy, which we define in our paper, has to be conserved. After you do this integral, you are also able to identify what is the microcanonical action. And it turns out to be exactly minus the area over 4G. And this all comes out in our paper. So
what you're trying to say is that these all these metrics which you contribute now after you integrate our T, including the fluctuations, should conserve the total off-shell energy.
Yes, but you see, it's exactly what you said, but there's one tiny rub that you might think that it's obvious, but it's not obvious in this context. None of this is on shell. And all of our definitions of energy are on shell. You know, an energy being a boundary term is an off-shell, is an on-shell statement. So you have to find an off-shell notion of energy for which this works. And that's why we have to sweat. Okay. But once you do that, and there is such a definition of off-shell energy valid for higher derivative theories and you name it, okay, you get that the microcanonical action is just the area divided by 4. and that you should look at perturbations that preserve this constraint.
So Wald had a paper on understanding stability of black holes, and in this context also, they define some notion of this canonical energy of perturbation.
Good.
Is it related to this discussion?
It can be related to this notion of energy, and it's related to the statement that I said previously that we expect the Schwarzschild black hole to be stable, and thus to be stable saddle also in the microcanonical ensemble. It matches with that, very much so. The work of Wald and others. Okay. In our approach, this stage just appears as a very, very abstract Legendre transform. It's not the same that Suresh was talking about. It's a slightly different one. Okay. It just appears as the conjugate momentum. That's how age appears. Okay. Why do we call it off-shell Hamiltonian? Well, we call it off-shell Hamiltonian because on-shell it reduces to the usual Hamiltonian. And also because there's a certain sense where it really matches the bulk terms. Because there's boundary terms that you have to be worried about, but the bulk terms really match the Hamiltonian that you get from general relativity. Okay. All right. What is the laundry list? Well, study the saddles of this thing at fixed energy. You find the Schwarzschild black hole. Okay. But here is a problem. This energy is a bulk thing. It's not a boundary condition. It's a bulk thing. And the thing that you're supposed to study perturbations of looks like a boundary term. It seems that it's upside down. Usually we think of boundary conditions as preserving something, but here it seems that it's upside down. And it's hard to work with this. So we do something else. Okay, check the paper for the details. We prove that second order perturbations of this can actually be related to second order perturbations of the action. It's not trivial, but it turns out it's true. With a constraint. Okay, the constraint is that those second order variations of the action now should preserve the area. And that's the boundary condition that you're missing. Okay. You again have to sweat a tiny bit, but just look at second order perturbations of the action, now restricted to not changing the entropy, not changing the area. Okay. So you drop this condition that the temperature is fixed at the cavity. What you do is that the entropy cannot change. Okay, at the bolt. There is another nuance to bother, which I think is one of the best nuances of the work. The Gibbons-Hawking-York term no longer vanishes. So you have to include it in the second order action. It's fun. We can do it. What are the results? Well, this is brand new. Again, we only discuss spherically symmetric modes. The lowest lying mode has a positive norm under G. So we should not be rotated. And look, it's positive. So in the microcanonical ensemble, Schwarzschild ADS is stable as it should. Okay. Now you might wonder, what about this nonsense of the complex modes? Are they still there? Yep, they are. Okay. Again, we find this mixture of real things and complex things merging in the complex plane, and it's the same thing. They're there. But again, all of the real parts are bigger than zero. So it's stable. So I'll come to my conclusions. We've made a comprehensive analysis of the stability of Euclidean saddles for the canonical partition function. We have studied the macrocanonical partition function for gravitational instantons. As far as I know, this is the first work that does this. Things that you can ask me after the talk. Can you do rotating black holes? The answer is yes. There's more ensembles you can do, and it's fun. Can you do anything inside the static patch of the sitter? The answer is also yes. Can you consider non-spherical symmetric modes? The answer is also yes. This is all unpublished work because me and Don are very busy, but all the calculations are done. Things that we have no idea how to do. Understand the Lorentzian path integral in C, in this complex space of solutions. We don't know. And with that, deduce our rule of thumb from a Lorentzian perspective. That's the holy grail. And we also don't know. And I apologize for overrunning in 5 minutes. I really don't like to overrun. All right. Thank you.
Thanks for this wonderful talk. Yeah. So, yeah, question time now.
I have time for questions if you want. There were some during the talk, but if you want more questions.
So can you kind of recover Wald's formula for high derivative theories in the microcanonical ensemble? in your setting?
You could, if you work perturbatively generically enough, which we haven't. But yeah, it would come out, which I think is cool. I mean, one of the things that I find really cool is this one here. When you have rotating black holes, you can work in the grand canonical ensemble, you can work in the canonical ensemble. And if you take a Kerr black hole, and if you ask, is it stable in the canonical ensemble? And the answer is, if you get close enough to extremality, it is. And you can ask the same question about stability of the rotating black holes in the grand canonical ensemble. In the grand canonical ensemble, is always unstable. So you should see a difference by changing boundary conditions. You should see that the negative mode disappears exactly where predicted by the specific heat changing sign in the Kerr black hole, in the standard Kerr black hole, which is a calculation that we definitely give sometimes in exams to our undergrads. Okay, and it's remarkable that it vanishes exactly there. By changing a single boundary condition, you see that instead of becoming always negative, no, it crosses exactly when the specific heat becomes positive. Okay, and the technology for deducing this, what boundary condition you should use in this case, is exactly what to be used for the microcanonical ensemble. And that for me really convinces me that we're doing the right thing, that this rule of thumb is not just by chance, because we do this, we do this for Kerr, black rings, you name it, and it always works.
This way of viewing the microcanonical ensemble essentially gives some notion of the so-called fixed area states that people sometimes use in discussions I've seen in, like in the relation between quantum information and radiativity. They use the fixed area states, and your area is fluctuating, and what is the total energy?
Yeah, in fact, you see, one of the authors of the work that I was just discussing is an author of some of those papers that talk about fixed area states, Don. And in fact, it was not a surprise for him at all that when we were talking about the microcanonical ensemble, that we were able to reformulate the problem in terms of perturbations that actually fix the area and not the end. It's weird, right? So what we're telling is that there's an equivalence between studying the stability of the area with respect to perturbations that preserve the energy. That's the same as studying perturbations of the action with respect to boundary conditions that preserve the area. And this statement, in fact, we use some of the technology of these papers, is precisely the statement that you're saying, that you look at energy preserving states. And in fact, the technology that we use, moving on to actually prove this statement, is part of the technology that he has developed with Shidong and others in Santa Barbara. I could not hear you very well, sorry.
Sorry. So the zero mode that can appear in this context, where you do not vary the area, which doesn't change the area while also keeping the energy fixed.
I think when you have a cavity, those guys are lifted. When you have a cavity, but that only occurs when you have a cavity. So the cavity helps you. The cavity helps you here. But we do worry about. I mean, we discussed the zero modes in our paper.
I see. I see. Interesting. Yeah. So, do you think some of the discussion that you have would be also important to, just a wild question, maybe to that you can import to the discussion on, say, entanglement wedges and stuff like that, because although they are not really cavities in that same format, but they are some kind of.
I think there's subregions, but I think it's different because here it's a boundary condition that we give, right? I think these discussions might eventually be relevant for some of our current understanding of the information paradox, in the sense that the way that we know how to recover information in a well-defined manner is at the moment, maybe this will change, but at the moment is by considering a region of flat space where nothing happens, where gravity is not dynamical, and then introduce a region where gravity is dynamical. This is at the moment, that's what we can do. And as soon as we introduce this region where gravity is dynamic, then it's a bit like a cavity. And then this becomes relevant because there's really a boundary condition. Having said that, as I hope I've emphasized, forget the quantum problem, okay? Just take the Einstein equation, just the Einstein equation, classical problem, and ask the following question. What boundary conditions should I choose at the cavity such that the Einstein equations are well posed, that I can solve them? And the answer is unique. And the answer is, for the type of boundary conditions that we're interested, which are stuff that is almost Dirichlet, you want to fix almost the cavity, nobody knows. It's a remarkable, super simple mathematical problem, which is an overwhelming number of people are researching it, for which we do not know the answer. I think this is, we should all be worried about it. If you put, the Einstein equations on a compact manifold, not compact manifold, sorry, on a manifold with boundary, and then on this boundary, want to decide what is the boundary conditions that I should give such that I can evolve this forward. The generic statement, we don't know. We know that it works for some, remarkably, but this is a result from 2022 by mathematicians from 2022. We know that the Rundall-Sundram boundary conditions work. And that's a result from 2022. And it's funny because they decided to study this because it was easy, not because of Rundall-Sundram. It's just because it was easy to do. But we don't know in general. Oh. So to get there, it's a huge open problem.
So basically, it's like classifying what kind of open boundary conditions you should have, or can work or something.
Yeah, like we don't know. And then
yeah,
we don't know which ones lead to a well-defined initial value problem classically, let alone quantum mechanically. Which I think, I don't know, I find this very distressing.
Very nice, very interesting. Very nice. The likelihood that you could be able to couple, like we had done some work where we were studying, say, ADS coupled to something by some coupling rules, so that the total energy is conserved, the energy of the holographic system plus the energy of the boundary theory together is conserved, and we have some well-defined coupling rules. So in principle, yeah, so we found a way to, so we have some way to say that if there's some iterative method, and practically when we do numerics and we find that this iteration convergence, and it's a very subtle problem though, it's an extremely subtle problem because the initial value problem is just works out in a magical way because you do not know a priori which initial conditions you will start with in many cases. And so
I think doing that at the full nonlinear level for generic data is completely out of question at the moment. I mean, even in ADS. So there's work by Helmut Friedrich in the 80s showing that if you fix in ADS where the conformal boundary is at infinity, if you have Dirichlet data, it's well posed. But that's it. Nobody knows anything else. As soon as you bring the boundary a tiny bit inwards, you're stuck. You already don't know what to do. In fact, I've been wondering whether these TT bar deformations could help you with this, because the TT bar deformations are supposed to bring the boundary inwards. But I'm not so sure if that will help or not.
Okay, so you can end the recording.
Sorry?
Maybe we had a recording, but we can continue informally.
Okay, then you stop the recording and I'll stop the sharing.